So today's topic is single application of single phase tripping and reclosing to the 380 kV double circuit transmission line. So we have three sections here. So section one deals about introduction of SPTR, and section two is about EMTP analysis, in which where we will be looking at the sizing of NGR, and also we will be looking at the resonance conditions that occur during the single pole tripping. And section three is about selecting optimum dead time for the circuit breaker. So this is a brief overview of this presentation. So let's move on to the section one. Here, in introduction, so let's understand what is single pole tripping. So why do we apply single pole tripping? The main objective of application of single pole tripping is to improve the system stability. So in addition to that, it can also be used to reduce switching over voltage in places. And where do we apply this SPTR? It is generally preferred in transmission circuits where we are transferring bulk amount of power, and the circuits which are crucial for system stability are uh, often embedded with this single pole tripping and after reclosure. So here, let me show. Yeah. So this circuit, can you see my pointer? Okay. I think you'll be able to see my pointer here.
Yes, yes.
Okay. So this is the example of how single pole tripping and auto reclosure helps you in maintaining system stability. Here we have a system to the left, and it is feeding the load with three parallel feeders, and there occurs a single line to ground fault in line 1. But the relay, in addition to tripping the line 1, it also trip or false trip the line 2. So in this case, if we have adopted triple pole tripping, then all the three phases of line 1 and line 2 would have been tripped. And you can very well see the curve C here shows that the system steps out of synchronism. Whereas when we apply single pole tripping and auto reclosure, even in case of this kind of false trips, we trip only the faulty phase. So we can see the curve B and C, A and B, where the system is still in synchronism. So this will give an insight into how the single pole tripping and auto reclosure helps us to maintain the system stability. So next, what is the advantage of single pole tripping? Because more than 93% of faults in transmission network are single line to ground faults. So whenever there is a single line to ground fault, we need not trip all three phases. Just tripping the faulty phase will help us to continue providing power to the load. And also it improves the system reliability of unshielded lines. It's even equal to the reliability offered by shielded line, where in a lower cost. So this is a low cost application, but it provides a reliability equal to a shielded line. So moving next, so how this single pole tripping and triple pole tripping, what's the difference between them? How do they help in isolating fault? So first, in case of a triple pole tripping, irrespective of faulty phase, all three phases will be disconnected. So when doing so, the arc current is being interrupted by the circuit breakers at the both ends. So the arc is interrupted and it is being fault is isolated. Whereas in case of single pole tripping, only the faulted phase is being tripped and open, whereas the other two phases are still energized. In this case, even after opening of the faulted phases, the arc current continues to flow. This arc current, which is flowing, after opening of the circuit breakers is called secondary arc current. This arc current is being supplied by the inductive and capacitive coupling of the healthy phases. So better I will explain this with example diagram. So to the left here, we have single pole tripping, the figure to the left, and figure to the right, I explain triple pole tripping. So in the single pole tripping, when there is a fault in the top phase, only the particular phase is being isolated. Whereas in the figure to the right, all three phases are isolated. So when you isolate the only the faulty phase, we can see that the faulty phase is being coupled to the healthy phases to these two capacitances. So these two interface capacitance continues to supply or feed the fault and which inhibits the extinction of the arc. So this can be very well understood from this EMTP simulation here. So the first figure here shows triple pole tripping where all three phases are tripped and de-energized. So to the right, we can see that there is no secondary arc. The arc is extinguished quickly, immediately after the opening of the circuit breakers. Whereas in figure 2, only the R phase is being tripped, and we can see that the Y and B phases are in healthy condition, the voltage is intact. But to the right, we can see that there is still secondary arc persisting for longer duration of time. So, so in overview, it is difficult to incorporate single pole tripping and auto reclosure because the fault will be continually fed by the capacitive coupling of the adjacent phases. So what is the criteria for extinction of the arc? So the criteria is just, we can say, law of conservation of energy. So to maintain the arc, if the arc loss is, if it's actually secondary arc is a free burning arc, it will sustain if the input exceeds the arc power loss. Otherwise, if the power loss in the arc exceeds the power input, then the arc will collapse and extinguish. So it basically depends on how strong this interface coupling is. So this interface coupling is what inputting or providing input to the secondary arc. So in our analysis, instead of analyzing the energy of the arc, we analyze the TRV and secondary arc current. So this graph here shows the criteria for extinction. So this shaded portion, uh, if the secondary arc and TRV is anywhere within the shaded portion, then the arc will be extinguished. So what are all the factors affecting the secondary arc? So the magnitude of primary arc current, that is the fault current magnitude, greatly affects secondary arc current, and the secondary arc current itself will affect the arc, the recovery voltage, the voltage which develops across the arc immediately after quenching of the arc is the recovery voltage. So that also affects the extinction and length of the arc. So all these four parameters depends upon the system design. That is the conductor arrangement, length of the line, circuit voltage. We know that the circuit voltage is directly proportional to the capacitance offered and also the length of the line. So in that aspect, the design of the system influence all these parameters. So what are the challenges in application of the single pole tripping and auto reclosure? First of all, it is very difficult to extinguish the fault in case of a long EHV lines. As we know, just now we saw that only the capacitance from the adjacent phase supplies the arc. So if it is a long line, the capacitance is big, so it will continue to supply the arc for a longer period of time. So the first difficulty is for longer lines, it's difficult to apply single pole tripping. Second is, yeah, as I said, it is proportional to length and circuit voltage. The magnitude of secondary arc current is proportional to length of the circuit and also circuit voltage. So as the voltage level goes up and also the length goes up, it's very difficult for applying this single pole trip. But this is actually unfavorable for this EHV and UHV lines. We go for EHV and UHV lines to ensure long distance power transmission in efficiently. So we go for high voltage. So this is exactly contrasting our basic requirement of high voltage and long lines. So the special control measures are required for this single pole tripping and reclosure in order to have a successful auto reclosure. Further, another difficulty is that often these long lines need shunt compensations. Once a shunt compensated line is tripped by single pole tripping, unbalance is being intentionally introduced into the circuit. So we intentionally trip only one phase of the circuit. So the now circuit is unbalanced. The tripped or de-energized circuit will form a resonant LC resonant. The line capacitance and shunt reactor forms a LC resonance circuit, and there is a high possibility of resonance occurring. So what are the control techniques? So what is the control technique to uh, reduce the single pole, reduce the secondary arc or the secondary arc current? There's nothing but neutralizing the interface capacitive coupling. So once we weaken the interface capacitive coupling, the arc will not be supplied for longer time. The arc will quench. So that's the objective. So what are all the ways in which it can be attained? One is using high speed at switch or ground switch. Another is transposition. The third one is four-legged reactor, that is additional reactor NGR to the neutral of the shunt reactor. So the first two options are not discussed here. However, NGR is widely used and it's almost mandatory because it also helps us to detune the circuit from resonance conditions. So we'll focus on the third option, NGR. So how NGR helps neutralizing this secondary of current? So the second capacitance or mutual capacitance between the phase CM. So if we draw expression for that, the capacitive current IAC is given by this expression, and the inductive current IAL is given by this expression. So by introducing this neutral reactor here during the fault condition, so the fault current will flow through the neutral reactors and this closed path. So we are injecting inductive current in phase opposition to the uh, capacitive current of interface. So this is how phase A to B. If the A phase is under fault and B and C phase, we inject capacitive current in phase opposition to neutralize the secondary arc current. So this is how the NGR helps in neutralizing the secondary arc current. So this is an example of single pole tripping of a compensated line without NGR. So if you see this figure, you can see that the arc is not extinguished for longer time. So the first figure shows here even up to 5 seconds the arc is not extinguished. So we can see this the nonlinear arc here. So it's still not extinguished. So we will not be able to reclose until the arc is extinguished. Whereas this is because of absence of the neutral grounding reactor. Whereas in second scenario, where we have introduced this neutral grounding reactor, this helps to neutralize the capacitive current from the adjacent phases and helps to neutralize the arc, and the arc quenches fast, and we will be able to see the recovery voltage in the phase, and we can reclose the corresponding phase. So what is, so how do we reclose? So why otherwise why secondary arc extinction is important for reclosure? Because the first figure shows we reclosing the circuit breaker after extinction of arc. So here the arc extincts, and after some time we reclose the breaker. So in this case, the voltage is recovered, a healthy voltage is observed after reclosure. Whereas if we reclose the breaker before the extinction of arc, say here, then the arc is reignited. So the arc will continue to persist, and we have to finally go for triple pole tripping and lockout. We cannot attend reclosure. So to reclose, to have a successful auto reclosure, the secondary arc extinction is very crucial. So this is a basic theory of why do we need single pole tripping and what's the challenges in single pole tripping. Now we move on to the analysis part. So in this analysis, our objective, we are very clear now, we need an NGR. So we need to find suitable value for the NGR. That's the first objective. And second objective is how long the secondary are going to take in our system. So that we can go for a successful reclosure. So estimation of dead time and sizing of NGR are the two objectives of the EMT analysis. So here the system we consider is a 380 kV system, and it's a double circuit. So it spans around 300 kilometer, and 60% of shunt compensation is being adopted. So this graph here shows with variation in the neutral reactance Xn value. Now we know our shunt compensation is 60°. So by varying the neutral reactor, so that we can choose optimum value of neutral reactor to enhance neutralization of NGR. So we can see that as the Xn value increases, as we move towards right, as the Xn value increases, we can see that these parameters, TRV, secondary or they all decrease. So so by choosing optimum value, we can go for selecting the sizing of the NGR. So here we choose 900 ohms. Why? Because so the induced voltage, you can see the blue curve, it decreases rapidly up to this point, and after this, the amount of decrease in induced voltage on open phase is less. It's not drastic. So that's one reason, and also the arc extinction time likely to increase after this point. So that's another reason. Also, we cannot have a high value of neutral reactor. We cannot keep on increasing the value of neutral reactor, because higher the value, higher the neutral voltage. So it will lead to requirement of higher insulation, so high cost. So I think that we'll also do see that in a slide. So now we have selected the NGO value through analysis. So what we have done is we have varied the neutral reactor value from say 6%, that is Xn by Xs ratio from 6% to 62%. We observed that 37% of Xn by Xs, that is 900 ohms, is optimum for successful neutralization of the secondary arc. So now, in addition to neutralization, whenever there is single pole tripping, unbalanced condition is being introduced into the system intentionally. So this unbalanced condition will lead to resonance of the line. That is, the de-energized shunt reactor oscillates with the de-energized capacitance through the capacitive coupling between the de-energized phase and energized phase. So this is the resonance condition. So condition for resonance is that any one phase is de-energized from the supply and it has a shunt reactor connected to that phase. So here, if you see this L phase is forms a resonance circuit. So it's been opened here. So when it is opened, this L and C forms a resonance circuit, and this resonance circuit is being supplied by the capacitive coupling of the from the adjacent phases. So this free resonance circuit will continue to oscillate, and this oscillation will not damp out because we have continuous supply from the capacitive coupling here. So this is a condition for resonance. So if we introduce a neutral reactor, so we will be able to neutralize this capacitive coupling current so that it has been the resonance condition is detuned. So here we have unbalanced circuit condition. So in single pole tripping and order enclosure, there can be two possible condition. One is one pole open, other is two pole open. So in one pole open condition, as we vary the compensation degree, the amount of induced voltage in the open phases, that is de-energized phase, increases, and you can see that it is around the resonant peak occurs around at 85% of compensation without NGR. So its value is around 900 per unit. So which is a humongous amount. So it cannot be allowed. Whereas interaction of NGR, you can see the blue curve here. So here an extend by excess of 15%, that smaller NGR when you introduce. So this resonant peak is being shifted from 85% to nearly 95% of compensation. So it helps to shift this resonant peak towards higher degree of compensation. And similarly, if we further increase the xn by xs ratio to 37%, again we have further shift. So there is no high induced voltage up to even up to 100% of compensation. So in our case, we have gone for 60% compensation. So we have a much less voltage, less than 1 per unit, much less than 1 per unit. So that is not hazardous to the system. Similarly, this is a graph for two-pole open phase condition. Here, I think the resonant peak occurs in a much lower degree of compensation, around 70 degree of compensation itself, a resonant peak occurs. Again, if we introduce NGR into the shunt reactor, it helps in shifting this resonant peak towards the right. So in both cases of open phase, one open phase and two open phase, so by introducing the NGR, we can shift the resonant peak to the right. So this is an example of resonance excited by single pole switching. So one pole is being switched here. So the first figure shows a high magnitude of over voltage. So around 729 kV in a 380 kV system. So it's a very high voltages cannot be allowed. So this is without NGR, the first figure. And the second figure is with introduction of NGR. You can see very well see the difference. The induced voltage or the resonant over voltage is under control. So it's far less. And this is an example of two pole open condition. So when two poles are open, so without NGR, we see much higher voltage. You can see around 1.1 mega volt in a 380 kV circuits, which is very high. It's not admissible. But with proper selection of or proper sizing of NGR, this can be reduced to much lower value, as shown the figure 2. So these two conditions are a series resonance condition that is occurring within a circuit. In case of double circuit, there is another possibility is that when one circuit is completely de-energized, there will be coupling from the adjacent energized circuit. So this whole circuit, de-energized circuit, will become a LC resonance circuit, and there will be continuous oscillation between this L and C, and these oscillations will be periodically supplied. Energy will be supplied by this mutual coupling. So again, we have another critical condition in a double circuit. A special attention should be made for double circuit lines. So there is three major conditions where this can occur. So one is the adjacent circuit is completely de-energized and there is no fault or any other contingencies. So in this case, we can see the equivalent LC circuit formed by this circuit, formed by this two double circuit. So the top is the energized circuit and this is the de-energized circuit. So this L and C will be coupled through this mutual coupling. So every phase will be coupled to the adjacent circuit and this forms a LC circuit. So now if there is no NGR, the first figure shows the magnitude of over voltage without NGR. So I think it's around 1.9 megavolt. So it's a very high induced over voltage or resonant over voltage is observed in this case. Whereas if we introduce a NGR here, then it is being detuned as, and then we have a voltage which is much lower. I think maximum of 137 kV, so which is less than zero point 0.5 per unit is what is the induced voltage in the open phases or the de-energized circuit. So another condition is that there is a fault, a LG fault in the de-energized circuit. So this actually does change the uh, configuration and the amount of capacitance involved with respect to the previous circuit. So now we have a different configuration of capacitance connected, value of capacitance. So the resonant peak will be different and the over voltage will be occurring at different point. So in this case also without NGR, we are observing about around 1.7 megavolts, which is very high. And with NGR, it's been controlled less than half a per unit of 141 kV. Similarly, another condition which can give a resonant point is that two double line to ground fault. In other words, double line to ground fault. Again, it changes the amount of capacitance involved or introduced into this equivalent circuit. So again, the point resonant, and one more resonant point will be there. So if the circuit is energized, then this can create unwanted thing. And here also we observe around 1.7 megavolts of over voltage. And with NGR, it's again controlled within less than a 0.5 per unit. So after selecting the NGR size, it's very mandatory to check this whether the size NGR is properly sized and it does not introduce any percent over voltage. So this various network configuration has been analyzed and ensured that there is no resonant over voltage. So having decided the NGR value and ensured that there is no resonant over voltage, then we can freeze the ohmic value of the NGR, and the insulation level of the NGR depends upon the neutral voltage. So the neutral voltage, we know it will increase with as the impedance increase. So we cannot have a very high value of neutral reactance. So upper limit for neutral reactance is the insulation level. Even though higher value of neutral reactor will give better performance or better arc quenching capability, secondary arc quenching capability, we are not allowed to have a very high value because it will consequently increase the cost of overall cost and overall insulation level. So this upper limit will be the insulation level. So through analysis, we need to find a new point where it is both are objective or achieved. So based on the system insulation level, so we can select it's just a voltage division. So we can select the neutral BAL insulation level. So we in first section we got introduced to single pole dripping. In second section we saw how NGR or neutral grounding reactor helps in enhancing application of single pole dripping. Now we need to find for the selected value of NGR what is the maximum time the secondary arc persist or the secondary arc current persist so that we can have a successful reclosure. So we need to wait until secondary arc quenches and we need to reclose only after the quenching of secondary arc. To do that, we study the various parameters that will affect the secondary arc. So basically, we check various network conditions. That is, what happens when the fault location is fault location is varied, and the effect of variation of circuit configuration. So the few possible configuration has been listed out here, but however, a lot of configurations permutations were analyzed, and also the effect of preloading conditions. So under all these conditions, the single pole tripping and reclosing were performed, and every time what is the time required for quenching of secondary arc was monitored, and the results are here. So this is we found that around the maximum time for quenching of secondary arc was around 232 millisecond. So this is the result of analysis of network conditions, load changes, and circuit configurations. So now we need to, so once the maximum arcing time is computed, then we can go on and decide the dead time setting for the circuit breaker. So as said earlier, even though we want to quickly reclose and improve the stability, but we cannot close before the extinction of arc. So that's why we need maximum arcing time is equal to the minimum dead time. So 232 is the maximum marking time. We can have the upper limit any value above 232, but any value below 232 is not permitted. So we can have any value above 232. However, the upper limit for this dead time is determined by stability of the system. So we need to check the stability of the system for the selected dead time. However, in our project, it was a mesh of the meshing was very good. So we have alternate paths and we didn't have any difficulties in maintaining stability. We were able to maintain stability even for 2 seconds of dead time. But however, it was not required to have that much time. So this is the relay operation. So once the ground fault is initiated, there is some particular time, considerable time is taken by the relay. So relay sensing and transfer trip. Once the trip signal is received by the circuit breaker, then there is finite time for circuit breaker to operate. Then when the contacts are fully opened, the arc will be interrupted. There is a duration of secondary arc. So this is the duration, maximum arcing duration that we have found from the EMT analysis. So in addition to this, we have to give a margin of 450 generally adopted for a deionization of the arc. So once the arc has been quenched successfully, still the air around the arc will be in ionized situation. So we need to give some adequate time so that the dielectric strength of the air around the arcing path is being recovered. So that for that we add a 450. So the dead time of the circuit breaker will be this secondary arc duration and ionization time. It is around 682 milliseconds. So for this circuit of 380 kV, 300 kilometer with 60% compensation, we found that the dead time required will be minimum millisecond. After that, the CB can be closed and a reclaim time was given for 1 second. So this graph here shows a typical reclosure scheme. So the first graph shows that the reclosure has been done after extinction of secondary arc, and as per this diagram. So there is a successful reclosure and the voltage has been developed and the system has returned to normal operating condition here. But whereas when we reclose the circuit breaker in advance before the extinction of arc, it's like the figure 2 here, the arc will continue to persist and there will not be any recovery voltage and the fault will not be cleared. So finally, then we need to go for complete isolation of all three phases by opening the all three phases, which will lead to stability issues. So in this way, the computation of secondary arc duration is very crucial for us to study the arc extension. For the application of this secondary arc, secondary single pole tripping and auto reclosure, we need some system requirements. So the relay should be capable of selecting the faulted phase and tripping the faulted phase alone. Selectivity of the relay should be enabled, it should be capable. It should be able to identify the faulted phase. It should be able to differentiate faulted phase from unfaulted phase. And also the circuit breaker should have independent pole operation. Mostly in EHV, UHV, we don't have a problem. Or always we have a single pole switchable. And the most important thing is the top footing resistance of these lines should be within the range of relay logic selection. Otherwise, we will not be able to differentiate single line to ground fault, or we cannot sense the single line to ground fault for high top footing resistance. So that's very crucial here. So to conclude, so the single pole tripping is quite easy for short lines. We don't have much difficulties. Whereas in long lines, we need to look into various situations, various conditions to have a successful reclosure. So therefore, EMT studies are required to determine the minimum dead time for successful reclosure. And when it comes to a shunt compensated line, the NGR sizing, to size the NGR, again we need EMTP analysis so that proper sizing can be done, and also we can control the resonant over voltage by properly detuning. So the NGR helps in shifting the resonant peak towards high degree of compensation again. So that's conclusion. And but still, we saw that a wide range of NGR can be used, but however, to optimize the NGR for the minimum dead time, again, the EMTP analysis helps because we saw that the arc time for arc quenching slightly started increasing after a particular value of xm. So again, this type of study helps to optimize the dead time also. So that's also very useful for from the analysis. Further, if there is any changes to the existing system, like the length of the system is increased or any voltage operating or etc., this will lead to change in the resonant peaks. And again, we need to carry out the detailed EMTP studies to have a successful implementation of or application of single port tripping and auto reclusion. Further, in addition to that, the relay settings has to be fine-tuned or appropriately made, like dead time, pole discrepancy, other settings has to be changed or fine-tuned to enable this single pole tripping and auto execution. So I think that's we come to the end of this session. Thank you very much. Yeah. So if there is any questions, we can.
All right, thank you.